All right, in this video we look at an example of a surface integral of a scalar function. And again, the notation for that is a double integral over the surface, some function f d sigma. Okay, and the meaning of this integral is that we need to integrate over uv space. We need to integrate our function evaluated at those points along the surface, and then we need to multiply by that by the magnitude of the cross product of the surface parameterization. Okay, so this is what we need to evaluate. We need to fill in the following blanks. We need to fill in the function. We need to find the area of a little part of the surface. And then we need to fill in the blanks for the UV parameterization. Okay, and so to do all that, we need some specifics about our surface and about our density function f. Okay, so here we can see that the function, they're calling it capital G here. Here is our density function. Okay, so that's the density changes only with this variable z. And here we have a description of the surface S. Okay, we can see that our surface is a cylindrical surface, so it will be good if we can remember the parametric form of a cylinder. And we can see here that the cylinder is in the YZ plane with x going from 1 to 4. Okay, so this says that we have a cylinder of radius 2 in the YZ plane. Okay, that's the y squared plus z squared. So this tells me that we need to let one of the variables be x, because x is going from 1 to 4. We need a circle of a certain radius, 2 in this case, and that circle needs to be in the YZ plane. So here are two parameters. U is the x variable, and we can see here that they're telling us that x needs to go from 1 up to 4. And v is the angle variable, and we need to figure out what that goes from and to. Now it looks like they're saying that z is bigger than 0, so we probably want only the top half of this circle, and that leads me to believe that we need to go, the angle needs to only go from 0 to pi. Okay, so the advantage of having a computer here is that we can double check our parameterizations. Let's do r of uv, and then let's create a plot of it. So before we even get to the integral part, the double integral part of the surface integral, we need to make sure that we have our parameterization correct. So let's do u for the x entry, 2 times cosine of v, and 2 times the sine of v. This should be our surface parameterization. But if we want to create a plot of that, parametric plot, we can plot this function, but we need to know what u and v go from and to. And since we can see here that we've assigned u in the x location, u is equal to x, and the problem says that x needs to go from 1 to 4. Because we are looking at only the top part of this circle, z being bigger than or equal to 0, I believe that v needs to only go from 0 to pi over 0 to pi. So we should see a cylinder in the correct plane. We should see it extending from an x value of 1 to 2, and we should see only the top part of it. Okay, so let me bring in my axes labels for the surface. And this should be a parametric plot 3D. And here we are seeing what we suspected, the top part of a cylinder. The x values range from 1 to 4, that's our u variable, u goes from 1 to 4. And in the yz plane, we're seeing a circle, but z needed to be positive, so we only needed to do half of the circle, the top half of the circle. So that means v went from 0 to pi. So there's our surface that we're dealing with. We have the parameterization correct now. Okay, We then need to find the function, the density function evaluated at those points on the surface. And we can see here that z is equal to 2 sine of v. And since our density function was z, we needed to evaluate it at those points on the cylinder, which was z is equal to 2 sine of v. So our density function is 2 sine of v. Okay, we know that from our formula for the normal vector to a cylinder, we need to compute the cross product of the partial with respect to u, and then the derivative of the surface with respect to v, and compute that cross product, right? And we are seeing the 0, so, and then the magnitude of that vector, so the magnitude of RU cross RV is equal to cosine squared plus sine squared, and we need to square the negative 2's, so that should lead to negative 2 cosine of v squared plus negative 2 sine of v squared, which is otherwise known as 4. So there's the magnitude of our cross product, and we're now in a position to do the double integral over this surface of the density function g, and that will be the double integral. X is our u variable, so u goes from 1 up to 4. V went from 0 to pi, that was the angle, and then we need to take the density function along the surface and then multiply it by the magnitude of the cross product, so that will be 8 sine of v du dv, and that is the double integral that we need to evaluate, which is a pretty easy integral to compute. I will get that answer worked up for you so that you know what you're shooting for. So we're going to do a double integral. We want to integrate from 1 to 4. We need to integrate 8 multiplied by the sine of v du dv. U was our x value, so that goes from 1 to 4. V is our radius variable. It goes from 0 to pi, and you can now find that that answer is equal to 48. And that would be essentially 48 kilograms if your density function, for example, was in kilogram per meter squared. Okay, so that would be essentially the units. So ends this video on an example of a surface integral of a scalar function, and all the other types of these problems go similarly. If you can spend your time and make sure that you get the surface parameterization correct. This is the key part of this problem, the parameterization itself.